This is Beyond the Business.
We spend most of our time talking about how to extract energy from coal and oil, from gas and uranium, and from wind and sunlight. We argue about fuels, technologies, efficiencies, and emissions, about what to burn, what to split, and what to replace. But very rarely do we stop and look at something much simpler. Energy is not only something we extract, energy already surrounds us at planetary scale, and one of the largest energy reservoirs on Earth is not hidden underground, not locked in fuel deposits, and not waiting to be mined. It is the ocean. Not the movement of the ocean, not waves, not tides, the ocean itself, water. Because water is not just a medium, it is a molecule that contains energy, chemically bound, stable, and everywhere. And with enough energy input, that molecule can be separated into hydrogen and oxygen. This is where the hydrogen conversation actually begins. Not in laboratory, not in industrial plant, and not in a policy paper, but in a simple physical fact. Hydrogen is not an energy source. It does not create energy. It does not exist freely in useful quantities. It does not solve anything on its own. Hydrogen is an energy carrier, a way of storing energy produced elsewhere, a way of moving energy through space and time, and a way of compensating for systems that cannot deliver energy when it is needed. And that distinction matters. Because most of the current hydrogen narrative skips this step entirely. It talks about hydrogen as a solution before admitting what problem it is actually trying to solve. Hydrogen did not become popular because it is efficient. It became popular because modern energy systems are unstable. Solar and wind are not failing technologies, they are intermittent technologies. They produce energy when conditions allow it, not when systems demand it. Hydrogen enters the picture as a buffer. Excess electricity is used to split. Water energy is stored in a chemical form. That energy is released later, somewhere else, sometime later. In theory, this creates flexibility. In reality, it creates a new system layered on top of an already complex one. Infrastructure, losses, water demand, compression, storage, and transport. Hydrogen is not the future of energy. It is response to the limits of the present system. And that is exactly why the industry is talking about it now. Not because it is perfect, but because alternatives are constrained, especially in sectors where electrification stops working. Heavy industry and long duration storage, and increasingly shipping. This episode is not about selling hydrogen and it is not about dismissing it. It is about understanding what hydrogen actually is, what problem it tries to solve, and what new problems it quietly introduces along the way. Because once we stop treating hydrogen as a miracle and start treating it as a tool, the conversation finally becomes honest. This is the ocean of waste. At some point, the climate race quietly changed its nature. What began as a search for physically workable pathways slowly turned into a competition of declarations. Targets appeared faster than systems, timelines moved ahead of infrastructure, and announcement arrived before capability. The problem was not ambition, the problem was sequencing. We began to announce transitions before we had the energy, materials, water, logistics, and governance to support them. And instead of slowing down to reconcile physics with the policy, the system did something else. It doubled down. When reality did not align with targets, the response was not to reassess feasibility but to search harder for alternative narratives that could preserve momentum. This is how a strategy turns into a dogma. A dogma does not ask whether something can scale. It asks whether it can be announced. It doesn't measure readiness, it measures alignment with the goal. And once a goal becomes absolute, every pathway that points toward it, even abstractly, is treated as progress. This is where new fuels enter the conversation. Not because they are ready, not because they are scalable, but because they allow the system to keep moving forward symbolically. Hydrogen becomes one of those symbols. It appears not as a proven solution, but as a placeholder, a promise that the gap between ambition and reality will somehow be resolved later. The climate race in this form is no longer about engineering sequences. It is about maintaining belief. Belief that scale will arrive. Belief that infrastructure will follow. Belief that physics will adapt to timelines. And this is why hydrogen is discussed the way it is today, not as a finished answer, but as a necessary character in a story that cannot pause. But before hydrogen became a climate solution, before it became a shipping fuel, before it became a symbol of transition, it had a very different role. To understand why hydrogen is everywhere in the conversation and why it struggles to exist in reality, we need to step back. Not into policy and not into targets, into history, into how hydrogen entered the energy system in the first place. Hydrogen was never the future. Hydrogen did not enter the energy conversation as a breakthrough. It entered it as a consequence. In the late 18th century, Henry Cavendish identified hydrogen not as a fuel but as a chemical curiosity, a gas that burned and turned back into water. The insight was fundamental, but the implication was clear even then. Hydrogen does not exist freely, it must be made. A few decades later, Michael Faraday showed that electricity could split water into hydrogen and oxygen. For the first time, energy could be stored chemically and released later. But notice what did not happen. No one called hydrogen a new energy source, no one spoke about replacing coal, oil, or steam. Hydrogen was understood for what it was from the very beginning, a carrier, a way to move energy across time and space when direct use was impossible. That understanding never really changed. When hydrogen reappeared in the 20th century, it wasn't in power grids or cities. It was in rockets. NASA didn't choose hydrogen because it was elegant or clean. Choose hydrogen because nothing else could do the job. Extreme conditions, no alternatives, maximum performance at maximum complexity. The same was true for fuel cells. They worked, but only where silence, reliability, or isolation justified the cost. And that's the pattern that matters. Historically, hydrogen has never been the default solution. It has always been the solution of last resort, used when systems fail to deliver energy directly. Which brings us to today. Hydrogen didn't become popular because it suddenly got better. It became popular because our energy systems became more unstable. Intermittent renewables, grid constraints, storage gaps. Hydrogen didn't arrive as a revolution, it arrived as a buffer. And that distinction changes everything about how we should talk about it. At this point, it's important to strip hydrogen of the hype and place it back into its natural role. Hydrogen is not a universal fuel, it is a specialist tool. It works best when three conditions are met: energy demand is concentrated, infrastructure is fixed, and alternatives are genuinely limited. This is why hydrogen discussions are regionally focused on heavy industry and chemical production, steel, fertilizers, and long duration energy storage. In these environments, hydrogen does not need to move across borders, it does not need to pass through multiple regulatory layers, it does not need to interact with thousands of independent operators. The system is closed, The variables are known, the trade offs are manageable. Shipping does not look like this. Shipping is mobile, distributed, jurisdictionally fragmented, and deeply dependent on global logistics chains, which immediately changes the equation. Because the moment hydrogen leaves a controlled industrial setting, it stops being a chemistry problem and becomes a systems problem. Production locations matter, transport routes matter, storage safety zones, ports insurance, and public acceptance all matters. Every added layer multiplies complexity. This is why, even in optimistic scenarios, hydrogen is rarely discussed as a fuel used directly on board ships. Instead, it appears one step removed, converted, stabilized, carried in another form. And that form is ammonia. When hydrogen enters shipping discussions, it almost never arrives alone. It arrives disguised as ammonia. Not because ammonia is ideal, but because hydrogen in its pure form is almost impossible to handle at maritime scale. Hydrogen has a fundamental problem. It is extremely difficult to store and transport. It requires either very high pressure, extremely low temperatures, or both. That makes it unsuitable for long voyages, large fuel volumes, and port to port operations. Ammonia solves part of that problem. It is easier to liquefy, easier to store, easier to transport, and it already exists as a global commodity, mainly for fertilizers. In other words, ammonia is not chosen because it is clean, it is chosen because it is manageable. But this choice comes with the consequences. Ammonia is not an energy source, it is not even a fuel in the classical sense. It is a hydrogen carrier, which means every ton of ammonia already contains the full energy and emissions history of hydrogen production behind it. And that history matters. If the hydrogen used to produce ammonia is gray or blue, the carbon problem is simply displaced upstream. If it is green, the system suddenly requires massive renewable overcapacity. Electrolysis at industrial scale, clean water supply, and additional energy to synthesize ammonia itself. Nothing in this chain is free and nothing is simple. Then there is a combustion. When ammonia is burned, it does not emit CO2, but it introduces other problems: nitrogen oxides, nitrous oxide, toxicity risks, and operational complexity. These are not theoretical issues and they are known chemical realities, which means ammonia does not eliminate risk, it replaces one set of risks with another. And this is the key point. Ammonia is not a breakthrough, it is a workaround, a way to make hydrogen fit into a system it was never designed for. A way to say zero carbon at the exhaust while moving the real cost elsewhere in the chain. This doesn't make ammonia useless, but it does define its limits. Ammonia works only if production is clean, scale is realistic, safety is tightly controlled, and the system around it is redesigned from the ground up. Shipping doesn't meet these conditions today, and that tension is impossible to ignore. Before hydrogen appears in engines, policy roadmaps, or fuel strategies, it exists only as industrial construct. Hydrogen does not exist freely in nature, it has to be extracted. And the moment we examine how hydrogen is produced at scale, the narrative changes. Hydrogen is created by separating water into hydrogen and oxygen. That separation requires energy, significant amounts of it. This immediately makes hydrogen dependent on electricity. Hydrogen production is inseparable from electricity supply. If electricity comes from fossil fuels, the logic collapses instantly. That is why hydrogen is always paired with renewables in policy discussions. But renewables are structurally unstable. Their output depends on weather conditions, seasonal patterns, and geographic location. This means hydrogen production can only be viable in specific regions where renewable generation is sufficiently consistent. That alone limits scalability. There is another layer that is rarely acknowledged. Renewable infrastructure is not immaterial. Wind turbines and solar panels have finite lifespans. After that, they become industrial waste, composite materials, large structures, limited recyclability. Before hydrogen is even produced, the system already accumulates long term material residue. Hydrogen production also requires water, not in symbolic quantities but at industrial scale. In regions with strong renewable potential, fresh water is often scarce. As a result, seawater becomes the primary input, and seawater cannot be used directly. It must be first desalinated. Desalination requires additional energy and produces concentrated brine as waste. That brine is discharged back into the ocean, altering local chemical conditions. Salinity increases, oxygen balance shifts, plankton and early marine life are affected. Coastal ecosystems begin to destabilize. Even when water is returned to the sea, it is no longer the same system. Its chemical and biological structure has changed. Now scale this process beyond pilot projects, not for demonstrations, but for continuous fuel supply. This is no longer a technical detail, it becomes an environmental system question. Water must be desalinated, then separated, then hydrogen must be compressed, liquefied, or prepared for further processing. Every step requires additional energy, every step introduces losses, and every step demands new infrastructure. Hydrogen does not replace an energy system, it adds layers to it. Electricity has to be generated, water has to be extracted, waste has to be managed. All of this happens before hydrogen performs any useful work. At this stage, hydrogen has not powered an engine or moved a vessel, yet the system has already produced industrial waste from renewable infrastructure, chemical waste from desalination, ecological pressure on coastal and river systems, and continuous energy demand. Hydrogen does not eliminate environmental impact, it relocates it upstream. Water does not regenerate at industrial speed, and coastal ecosystems don't adapt on engineering timelines. Rivers and deltas are living systems, not neutral buffers. When water is extracted at scale, something else gives way. This is why hydrogen cannot be treated as inherently clean. It may appear clean at the point of use, but the system that creates it is resource intensive, environmentally intrusive, and structurally complex. Before we talk about fuels, engines, or emissions, this reality has to be acknowledged. Hydrogen is not a simple alternative, it is an industrial construct, and its environmental cost begins long before it is ever used. So, if hydrogen is already difficult to handle at scale, the next logic step becomes obvious. You don't move hydrogen directly, you convert it. And this is where ammonia enters the picture, not as a breakthrough and not as a new idea, but as a workaround. In practice, when the industry talks about hydrogen for shipping, it is rarely talking about hydrogen itself. It is talking about ammonia. Hydrogen bound into a molecule that can be stored, transported, and traded using systems that already exist. This matters because ammonia is not a future technology, it is one of the oldest large scale industrial products in the world. For more than a century, ammonia has been produced through the Haber Bosch process, not for energy but for fertilizers. Entire ports, pipelines, terminals, and safety regimes were built around that purpose. That history is exactly why ammonia looks attractive today. The infrastructure is familiar, the logistics are known, and the trade routes already exist. From a distance, it looks like a shortcut, but when you move closer, the weight of the system becomes visible because ammonia does not appear on its own. First, hydrogen must be produced. Then, nitrogen must be separated from air. Then, both must be forced together under high pressure and temperature in continuous industrial operation. This is not a flexible process. It does not like interruptions, does not scale gently. It demands stable energy input, stable supply chains, and permanent control. In other words, ammonia does not simplify the hydrogen problem, it packages it. And packaging has consequences. Every additional step adds energy loss, every additional step adds infrastructure, every additional step adds risk that must be managed not once but continuously. There is also a practical shift that often gets overlooked. Ammonia is not just a fuel candidate, it is a toxic industrial chemical. That single fact reshapes everything around its use in shipping. Ports must accept it, crews must be trained for it, emergency scenarios must be rewritten, liability frameworks must expand, and public tolerance must be negotiated. Even when everything works as designed, the system carries more weight than before. Not because ammonia is evil, but because it demands permanent attention. So ammonia becomes a mirror of the broader problem. It exists not because it is ideal, but because it is manageable within existing industrial logic. It is not the destination, it is a bridge built out of necessity. And once we recognize that, the next question becomes unavoidable. If hydrogen already required extraordinary effort to exist, and ammonia adds another industrial layer on top of it, what does the full balance actually look like once we follow this path all the way through? That is where the analysis has to go next. Up to this point, the conversation around hydrogen and ammonia has been framed very carefully. We were told where emissions disappear, we were shown where CO2 drops to zero, we were guided toward the exhaust pipe and invited to stop thinking there. But energy systems don't begin at the exhaust, and environmental impact does not end with what leaves the funnel. If we want an honest comparison, we have to step back and follow the full path from origin to use and beyond. Because what is being sold as a clean fuel is only clean at one specific point in the system. Everywhere else, the footprint quietly accumulates. Before ammonia reaches a ship, it already carries a long industrial history. Electricity had to be generated, not abstractly, but physically. Water had to be extracted, treated, and altered. Infrastructure had to be built, operated, and eventually discarded. Energy was consumed again and again, not to move cargo, but to make the fuel itself exist. None of this disappears because the exhaust is CO2 free. It simply happens upstream. This is where the framing starts to crack. Ammonia does not eliminate environmental pressure, it relocates it. Instead of emission at the point of use, we get pressure on water systems, chemical alteration, coastal zones, industrial waste tied to renewable infrastructure, and permanent energy demand layered on top of existing systems. And then the fuel finally reaches the ship. At the exhaust, carbon dioxide is absent, yes, but absence of CO2 is not absence of harm. Combustion of ammonia introduces a different set of realities. Nitrogen oxides appear, nitrous oxide emerges greenhouse gas with a far stronger warming effect than carbon dioxide. Ammonia sleep becomes a risk, toxic, corrosive, and dangerous to both crews and ports. This is not theoretical, these are known chemicals outcomes. What changes is not the existence of damage, but its form. With fossil fuels, harm is familiar. It is measured, regulated, and increasingly optimized. The system is far from perfect, but its behavior is understood. With ammonia, harm becomes more complex, more distributed, harder to model, harder to control, and far more sensitive to operational failure. So the comparison cannot be reduced to a single line about carbon. What we are really comparing is this: a mature system with known damage and established controls versus a layered industrial construct that replaces visible emissions with the hidden complexity. And that is the moment where the narrative collapses. Because green in this context does not mean harmless, it means selectively clean. Clean at the exhaust, opaque everywhere else. Once the full chain is visible, before the pipe and after it, ammonia stops looking like a solution. It starts looking like a trade. A trade where one problem is removed from sight while several new ones are introduced upstream and downstream. This doesn't make ammonia useless, but it does make one thing clear. It is not a clean break from the past, it is a rearrangement of impact. And when a system is rearranged rather than resolved, the question is no longer whether emissions move to zero at one point, but whether the system as a whole actually improved. That question cannot be answered by slogans, only by structure. And once structure is examined honestly, the illusion of clean fuel no longer holds. After everything I have mapped, the conclusion is not that hydrogen is bad. The conclusion is that hydrogen is being asked to do a job it cannot do at scale. It is being used as a placeholder for stability, a way to keep the climate race moving without admitting that the fuel answer is not ready. Because in shipping, the question is never can we make a molecule. The question is can we build a global system around it with the ports, bunkering, safety zones, emergency response, and a supply chain that must be stable and not aspirational. That is what turns a fuel into infrastructure. And right now, hydrogen only survives in the conversation by staying inside a narrow frame. Zero CO2 at the exhaust. But shipping doesn't operate at the exhaust, shipping operates across the full chain. So once you include the full chain, the fuel stops looking like a solution and starts looking like a trade. A trade where one visible problem is reduced, but the system becomes heavier, more fragile, and harder to govern. That does not mean ammonia has no role. It may work in specific corridors under strict control and in controlled volumes. But that's not a global fuel transition. That's a niche tool. And the danger is not hydrogen itself. The danger is the industry locking its future into a pathway that still depends on the perfect conditions. Because shipping cannot be built on perfect conditions. It is built on friction, delays, politics, congestion, and failure modes. So the real conclusion is simpler. Shipping does not have a fuel solution today. It has governance problem today. And until governance improves, every new fuel becomes a distraction, expensive, complex, and politically convenient. The fastest emissions reduction available right now is not a new molecule. It's better scheduling, less idle time, less congestion, better utilization, better planning, and better systems. Only after the system is tightened, stabilized, and governed properly does the fuel question become meaningful. Until then, hydrogen is not the future. It is a story we tell to avoid admitting we don't have one. So, where does this leave shipping in reality? It leaves the industry in an uncomfortable but necessary position. Shipping is not failing to transition because it's conservative or resistant. It is failing to transition because there is no fuel today that can honestly deliver what has been promised. The fuels presented as green are only green within a narrow frame. They look clean at the exhaust, but when we extend the boundary before the pipe and after it, the picture changes. Ammonia does not emit CO2 at combustion, but it introduces other emissions, some of them with stronger warming potential. It carries toxicity risks. It reshapes safety ports, insurance, and liability. And it depends on upstream systems that are neither clean nor scalable today. This is not widely understood because the dominant narrative has been simplified to one variable, CO2. Zero at the exhaust became the story, everything else was pushed out of sight. But shipping does not operate at the exhaust level, it operates at system scale. And at that scale, ammonia is not clean replacement, it is relative substitution. One form of impact exchanged for another. That creates a second problem, pressure. The industry is under growing pressure to carry a green label, to announce transitions, to signal alignment. But when fuels themselves are not fully green, those announcements become a reputational risk. Promising a future built on ammonia or similar fuels assumes something that is not yet true, that the fuel system is ready. It isn't. Which raises a more honest question: should shipping be forced to claim zero when zero does not exist in operational reality? Or should it be allowed to work within a framework that reflects how systems actually behave? This is where network zero matters, not as a retreat, but as a correction. Network zero does not ask a single actor to erase impact, it asks each actor to define their real position in the system and to optimize within it honestly. For shipping, that means operational efficiency, routine, speed, cargo planning, governance, and transparent boundaries. Not imaginary fuels and not premature promises. Shipping is not a battery powered car, even batteries have a footprint. They must be produced, they must be charged, and the system behind them still emits. At planetary scale, nothing is free, nothing is zero, only better or worse organized. And when all current options are examined without illusion, one fact remains unchanged. The only energy source that genuinely breaks the fuel loop, rather than rearrange it, is nuclear. Everything else is a workaround. Until that reality is faced, fuel transitions in shipping will remain symbolic, expensive, and fragile. And the real progress will not come from changing what ships burn, but from changing how honestly the system defines its limits. That is the point where the conversation must move next.